FEDD project, completed by Brian Garcia, Robert Bolin, Kelly Snyder, and Alex Theodorakis.
Our mission was to build a precision launcher capable of hitting a target 30 feet away. We needed to incorporate 2 transfers of energy and uphold a 4 foot by 4 foot by 4 foot dimension requirement. We started off by incorporating the design cycle into our project. We first defined the problem and searched for solutions to it. Then we narrowed down our ideas and started building prototypes. We faced a few initial problems. The first was how to convert potential energy into useful kinetic energy. Second was creating a design with minimal resistance that would maximize the energy used. We also had to figure out how to make it as accurate as possible and how to make the load time quick and efficient.
This picture shows the first step to building our project. It is 2 parallel towers held together by 4 pieces of wood. There's also a foot at the bottom on both sides to make sure it's stable while the weight is pulling down. This picture shows our initial problems and how we dealt with them. We first needed to convert potential energy to kinetic energy, so we have a tower that will have a dropping weight pulling the string. Also, this is a very sturdy design. It was meant for the accuracy to be impeccable. Also, it would ensure that we had quick load time, solving all of our initial problems. Here we see the pulley system. There is a pulley at the top of the tower, and this is the pulley at the bottom of the tower. The weight would drop from the top, pulling the string through the first pulley, and then through the second pulley. This is the essential pulley because it turns the vertical into horizontal pull.
In dealing with our first problem of converting potential energy to useful kinetic energy, we decided to make a tower with a 2-pulley system. We would attach the weight to a string through the 2-pulley system and drop it from the top of the tower. In our second problem of creating a design with a minimal resistance, we would attach the swing arm to a dowel and let it swing freely instead of with the dowel. In our third problem of making sure it was accurate, we would use a fixed catapult design, which is where the swing arm hits a block every time. That way it ensures that the projectile will hit the same spot every launch. In our fourth problem of the load time, we decided to loop the string around a hook where we could cut it easily when it got to the right height. In the build phase, we built our tower and our catapult separate, and we would attach them later with the base. The tower we tested separately from the catapult, which worked flawlessly, while the catapult failed miserably.
This is our initial design with the catapult idea. The catapult would have a similar tower to the one in the back, and it would have a swing arm attached to a dowel at the bottom of the tower. We would use a resistance band to pull back to create the force that would launch the projectile. Later, in testing, we found out that the weight was not enough to pull the arm back, so we had to scrap the whole idea and start over again.
The problem with our catapult was the resistance band we had bought was too strong for the 5-pound weight. It would just simply not pull it back. And also, it was bulky, and the swing arm wasn't as efficient as we wanted. To solve that, we tried using a rubber band, which also didn't work. So we completely scrapped our idea and made a slingshot. And with this slingshot using a rubber band, we would take a different type of projectile and shoot.
This picture shows what became of our final design. We still have the tower and the pulleys, and we've incorporated the slingshot on a base that could be adjusted for angle.
For building and testing, we built the new design using the slingshot and rubber band. We tested 3 separate angles of the trajectory in order to hit the target. Once we found the correct angle, we executed a few more tests in order to confirm consistency. We also worked out the best method to drop the weight.
This is the final assembled design. It has a slingshot, a release mechanism for the slingshot, and the weight and string. Also, the slingshot is on a base that is adjusted for the distance and the target.
Freshman Engineering Design Day. Our first attempt came up short. Adjusting where to drop the weight from our second attempt was a success. Finally, our last attempt strayed left but had the height and distance. Overall, our project design did what the rubric asked of it, and we considered it a success despite not placing.
This is the FEDD reveal. After going through the design cycle, we have arrived at the final design, and it works perfectly. We didn't place, but we did hit the target, so we accomplished our goal.
Wrapping it all up. If presented with this again, we would exhibit better time management. We would like to advise freshmen to orientate themselves with the craft center as early as possible because it may be an inconvenience come crunch time.